Okay, so I have 3 pictures in the notes. I might just do one of them because, I'm on a chalkboard, but I just want to maybe talk through, maybe if you don't understand what I'm saying in my notes. So this first goal is to draw this super simple idea of what a pump is. So I'm going to do a radial one, or centrifugal. Okay, I have an axial one, and then I have the windmill also in the notes. I might just draw them out, but so this is just kind of important to see. If you just draw sort of what's going to be happening, interesting things happen. Okay, so for these radial ones, you send fluid in right in the perpendicular plane. So this is an XY plane right here, so it's flowing in the Z coordinate, all the flow rate. Okay, and then it's kind of hard to imagine, but you got to understand that there's there's some impeller sort of happening right here. Sometimes there's curves, right? But you're sort of right. The idea is you're cutting your centrifugal pump directly in half, and you're just projecting and seeing what this blade or impeller looks like. Okay. So it's kind of hard to see, but we'll do our best because we're drawing simple pictures. Okay, and the idea is this is where the energy comes into, because this has some radial velocity in the Z direction, or you could think of it as a torque is applied to the pump, and torque you can get to power. So we'll think about torques pretty soon here. So first thing is think about how fluid is entering in this Z direction, and it hits the XY plane, and then it starts to bulk up or decelerate. So if I have a du, what do we know from that? So if this is going to be decelerating, that means I have a pressure rise. It makes sense just because you're throwing a bunch more fluid mass into this XY plane, so it has to decelerate, and then what happens is it spins and spins and spins, and it exits in the XY plane. So it's kind of hard, but really there's this, because this is the XY plane, this is the Z coordinate, you have to understand the fluid's coming out of the board or into the board in this scenario. So it's that balance of you're applying a torque, you're creating a rotation, you're sending fluid into the XY plane, it decelerates, that increases the pressure, you rotate it at an angular velocity, adding rotational energy. That rotational energy is then transferred in kinetic energy, which forces it out of the pump, and that's actually more kinetic energy. So that's the goal. Centrifugal pumps you turn your rotational energy and kinetic energy, which rises, gives you a head rise, gives you an increase in energy to your fluid. That's maybe just talking over. So if I then take this and then flip it over this way, so now I'm going to look at the XY plane. Maybe you can see this a little more. Like that. So this is now the XY plane. So now we can really get a sense of what the impeller is. Fluid's coming into here, Here's the fluid flowing in from the input to the centrifugal pump. It's flowing right into there, and then as it gets there, it's then going to be swung and it's going to be swung and flown outward due to the rotation. So that's where these impellers come into play, So how do I draw them? These ones. So think of it as something like that. This is where a whiteboard would be helpful, but what are you going to do? So, this is what I was talking about. See how the outflow of this centrifugal pump is in the XY plane. Fundamentally different from an axial flow rate if I draw the next picture. Okay, what else do we see about these things? Well, again, clearly there's some diameter to this impeller. The diameter will then get you a radius of this, or a total radius of the impeller that you have. Okay, but again, these are easier to measure, so it's good to put things in that quantity. What else do we have? Well, here you can see that there's a difference, There's a DR, what do they call it? Yeah, DR. right? So there's some tiny contraction here and big, right, and larger out there. Okay, and you have to think of this, right, as since we're looking in the XY plane, fluid came into here, slowed down, and now has to move out, right? So that's this, right? This is sort of an increase in cross-sectional area. You could think, right, think of it that way. These are hard pictures to draw because you have to think of the fluid going into here, decelerating, and then moving out as it flicks out forward. And there's even this expansion thing that's going to be happening. And then the final stage is then flowing out this way, and now your outflow is in the XY plane, whereas the inflow is into the Z direction itself. And again, right, there is an angular velocity for every single pump that we have, axial, radial, or even a windmill. It's something that you definitely should measure or try to quantify. So this idea of the propeller, some geometry or some parameters based on this parameter of the impeller has to matter. If it was flat versus some curvature, there's going to be something different about it, and that's what these equations are talking about. Okay, look at an axial flow now. I'll just do them all. How about that? It's on YouTube. Y'all have time. Let's look at the axial pumps, and those are the pumps you put in your window when it's too hot in Portland and you don't have enough for AC. So look here, this is now a YX coordinate system. And now I'm doing the exact same thing where I'm going to sort of just cut it directly in half. Here's sort of these are the impellers, right? So again, if you just took your box fan and just looked at directly through there, you see that you'd have some look like this, where this is the motor, right? That's your motor. These are the impellers. What else? So then right, and then what you're going to be having now is you have something where, where's the back and front? So we have flow, right? This is what's happening for axials, right? Not a lot of motion, not a lot, right? Almost zero effective fluid motion out here. It spins. Right? That's what your fan's doing, right? You put your hand behind the fan. There's a little bit of section. It's not too big. You put your hand in front of the fan. It's like, wah. So that's what you're seeing for axial flow fans. They take it and they just move it down really quickly, right? And notice the big difference is that you're in the Z coordinate. The fluid entered in the Z and exited in the Z coordinate. There was no change of XY plane. But it's interesting to see there is sort of an underlying, you think like, well, that doesn't make sense. Like something, there should be some similarities between these two things if they're all working. If I do the same thing now, right? Now, again, right, keep comparing to just the previous example I had where I looked at a fuel pump, right? And if you do it this way, something like this, right? Right, still have myself a radius, right? Still have myself an angular velocity. But then if I look in the front of the brain, in the front or the back, you'll notice before, right, the impeller was just a line. Right, but for axial, you'll see that it's also right. You'll see that there's also some width to it. This is not where fluid enters. This is actually the impeller. So for an axial fan, that's how it's actually doing. And if you looked in like all of the radial coordinates, right, is that the impeller itself right? So the impeller actually has a dimension in all of the variables, right? In the simplified model for the centrifugal, you just kind of had this thickness blade that went through it. But in terms of these axial fans, you'll see they always have a curve in them, and they'll take up physical dimension in all of the spaces. So they're always in contact with the fluid. is one of the bigger things. So bigger thing with these, I think I went over that, where for the axial fans you have slow flow rate going in and then bigger flow rate going outward. And then same thing, you put energy into the motor. You plug it in, that causes this DC motor to move, or AC motor to move fast. That's the power you put in. You take that power and you accelerate fluid because of it. There's another one for a windmill, but the windmill is just the exact same as the axial flow fans. The only difference is they're doing the reverse. They're taking a lot of fluid flowing in. They have a different geometry of the impeller, and that decelerates the fluid, and they take energy away from the flow field. So I'm not going to draw the image of a windmill, but I think that's enough examples of just showing you how drawing these pictures gives us a sense of what parameters we should really look at and what equations we should draw in the first place. How about this? I was thinking about this earlier. How about a nice extra credit? Find turbo machines in your house. Take some pictures of these components, right? And how about you measure the impeller diameter of them? It's not analytical or any theoretical, but maybe get a sense that these turbo machineries are everywhere and we use them all the time. It could be in your car, in your house. Just find some. Take a screwdriver, take it apart, and maybe just try to look at what these parameters would be. Give me as many dimensions as you want on the impeller, and you'll see later that that's pretty important. And maybe take pictures and identify what the components are. It's pretty fun to connect maybe the concepts we learned to what's in your house. So, extra credit.